Good afternoon, students. Next we pass on to the 9th unit, that is Kinetic Theory of Gases. It's a very small lesson, and in this lesson we are going to see first what is a kinetic theory. You know what is a thermodynamics? It's basically a macroscopic science, and the thermodynamics deals with the pressure, volume and temperature. So the kinetic theory relates all these things together. For example, it's a sample of a gas we are taken, and for that gas, what is a molecular motion, how the pressure and temperature has to be related, and that is things has to be given in this chapter. Now we pass on to in this unit, the next thing is pressure exerted by a gas. So how the pressure has to be exerted by a gas? For that we are taking a monoatomic gas. Monoatomic means it's a single atom. So we are taking that type of gas. For n molecules it will have, and each will have the different masses, and that mass will be taken as a m, and inside of it will be taken in a cubical container with a length of L. And what happened to these atoms and what happened to the molecules? So the molecule of the gas, what happened means it will be moving in a random motion, and if there will be a random motion, definitely it will be collide with each other, and also it hit on the walls. So as the collisions are elastic in nature, definitely there is no loss in the kinetic energy, but some momentum will be occurred there, and that the molecule of the gas exerts a pressure on the walls due to that collision on it. So during each collision, the molecules will have certain momentum to the wall. So due to the transfer of momentum, the walls experiences a continuous force on it. So that force experienced per unit area of the walls is container that determines the pressure has to be exerted. So we know that what is a pressure is nothing but force per unit area. So in particular area there will be a continuous force, means there will be a pressure has to be exerted, and it is essential to determine that the total momentum transferred by the molecules in a short interval of time. So a molecule of a mass m moving with this. So now the molecules are moving, it will be moving with the mass m, and if it moving, it will have some velocity, and that velocity we are taken as a v, and it will have the three different ways, and that three different axes we are taken as a x, y and z, and for the different velocities for the three different axes has to be taken as vx, vy and vz. That will be hits on the right side wall, and since we have assumed that the collision is elastic, so the particle rebounds with the same speed and its x component is reversed. That means only the x component of molecule will go and hit, and it will be rebounded. What is the meaning of rebounded? It goes in one direction and hit again, it will be coming on the same way but opposite in direction. So we are taken that x component has to be a reversed one. That's why we are taken that as a negative, and that is v minus vx, vy and vz. So for that x component of the momentum for the molecule before collision is mvx. So obviously after collision that will be minus mvx. So the change in momentum of the molecule in x direction, so final momentum minus initial momentum, that will be taken as minus vx minus vx, that is equal to minus 2 mvx. So according to law of conservation of a linear momentum, the change in momentum of the wall is nothing but 2 mvx. So the number of molecules, like it will be hitting the right side in the same time interval, small time interval, that is del t, and for that the molecule within the distance of vx del t from the right side wall moving towards. So what is the distance? Distance velocity is nothing but distance by time taken. So we had calculate the distance, means it is velocity into time taken. Here we are taking the velocity in the x direction as vx, and the time taken we are taken as a very small time interval, that is del t. So distance is nothing but vx into del t, and that it will be hit on the right side of the wall, and the right will hit on the wall in the time interval of del t. The number of molecules that will hit on the right side wall in the time interval of del t is equal to the product of the volume. So what is volume? Area into sum of the distance, and that is A into Vx del t. And the number density of the molecule n, that this small n indicates the number density of the molecule, and capital N denotes the number of molecules. You have to differentiate what is the two different value. And now A is the area of the wall and n is the number of molecules per unit volume, that will be taken as capital N by V. So we have to assume that the number density the same has to be throughout the cube. So now all the N molecules will move to right, and therefore what is the average? Only half of the N molecules. So we have to assume that before we are only assuming all will be moving on the right side. But actually what happened means only half of the N molecules has to be moving on the right side. So we are taken that as a N by 2. Okay, because half of the N molecules. So the number of molecules that hit the right hand side of a wall in a time interval of del t is nothing but n by 2 avx del t. So the same interval of time del t, the total momentum transferred by the molecule is nothing but that is del p is equal to n by 2 avx del t into 2 mvx. So from this we are cancelling the 2 and we'll get that we a Vx square, Vx into Vx square and m and then n into del t. So from the Newton's second law, the change in momentum in a small interval of time t, so that will give the rise to the force, that is a force exerted by the molecules of the wall, that is del p by del t. So it will, the equation will be the del t and del t will get cancelled and that will become nmavx square. So pressure is nothing but force divided by the area, and now we are substituted in this, so a will get cancelled. Again you are getting the simplified equation, that is nm Vx square. Since all the molecules are moving completely in random but they do not have the same speed, so we can replace the term Vx square by the average of Vx the bar in equation. So that is, the gas is assumed to move in a random motion but it has no preferred motion direction of motion. So it implies that the molecules have the same average speed in all the three directions. So Vx square bar is equal to Vy square and then Vz square. So that means V of square is equal to Vx plus Vy is Vz, that is equal to, that is all the things will be equal to Vx. So Vx plus Vx plus Vx will give 3Vx bar square, and then Vx bar square and 6 by 1 by 3 V square, and we are substituting this in the value and we will get the simplified equation as P is equal to 1 by 3 N by V M V square bar, and this small n is nothing but capital N by capital V, and that will be changed as small n. Okay, and this following inference can be made from the above equation, that is pressure exerted by the molecule. See, from the equation itself you know the pressure exerted will depends on what? First of all, it depends on the n, that is the number density. It implies that the number density will increase, obviously the pressure will increase. So what is the next thing? That is a mass. If the pressure arises due to the momentum transferred to the wall, larger the mass will have, the larger momentum has to be fixed. Okay, that will be, the pressure will increase if mass is more. And the mean square speed, if for a fixed mass, if the increase the speed, the average speed will also increase. So the pressure will increase, the average speed also increase. Okay, so for simplicity the cubical container is taken into the consideration. So the above result is true for any shape of the container as the area A does not appear in the final expression. So the pressure exerted by the gas on the molecules on the wall is independent of the area of the wall. So this is a pressure exerted by a gas. And next, followed by this, with the same equation, we are going to interpret the kinetic interpretations of the temperature. To understand the microscopic origin of a temperature in the same way, we can rewrite the equation, that is P is equal to 1 by 3 N by V mv square, right? So in this, if we are multiply this with the volume, you will get PV is equal to 1 by 3 Nm V square. So we are comparing the ideal gas equation, that is PV is equal to nRT. Here we are taken the constant as K. So this is nothing but PV is equal to nKT. So nKT is equal to 1 by 3 Nm V square. So KT is equal to 1 by 3 mv square. So multiplying both the sides by 3 by 2 and we will get 3 by 2 kT is equal to 1 by 2 mv square. So now the RHS of the equation is called average kinetic energy of a single molecule. So the average kinetic energy per molecule is nothing but Ke is is equal to 3 by 2 kT. So this implies the temperature of the gas is a measure of the average translational kinetic energy per molecule of the gas. It's also very easiest one. It's important result from the kinetic theory of gases. Okay. And from this what we are inferring that the average kinetic energy of the molecule is directly proportional to the absolute temperature of the gas. And the equation gives a connection between macroscopic world, that is a temperature, to the microscopic world, that is a motion. Average kinetic energy of each molecule depends only on the temperature of the gas, not on the mass of the molecule. In other words, if the temperature of an ideal gas is measured using the thermometer. So the average kinetic energy of each molecule can calculate it without seeing the molecule through the naked eye. So multiplying the total number of the gas molecule with the average kinetic energy of each molecule will get the internal energy of the gases attained. So what is the internal energy of ideal gas? U is equal to N of mv squares, that is U is equal to 3 by 2 nkt. So from the equations we will get that we understand that the internal energy of an ideal gas depends only on the absolute temperature. It's independent of the pressure and the volume. And next we pass on with the same relation, that is a relation between the pressure and mean kinetic energy. From the earlier section we know that what is the internal energy, that is U is equal to 3 by 2 nkt. Above equation is also written as 3 by 2 nkt is nothing but PV. So PV is equal to nkt. So we are replacing that, we will get U is equal to 3 by 2 PV. P is equal to 2 by 3 U by V, that is 2 by 3 U. So we can state that the pressure of the gas is equal to 2/3 of the internal energy per unit volume, or internal energy density, that is U is equal to U by V. Writing the pressure in terms of mean kinetic energy density, so we will get P is equal to 1 by 3 nmv square, that is 1 by 3 rho v bar square, that is rho is nothing but nm, that is mass density. Note that n is a number density. Multiplying and dividing the RHS of the equation by 2, we get P is equal to 2 by 3 rho by 2 v square, that is P is equal to 2 by 3 rho by 2 rho v square, that is 2 by 3 Ke. And from the equation the pressure is equal to 2 by 3 of mean kinetic energy per unit volume. Okay, so this is the relation between the kinetic energy and the pressure.